Well, we did double angle identities. If you can get an angle involving double angle identities, maybe it follows that you can take half of that and get half angle identities. Does it? Here's a double angle identity. Cosine 2 alpha is cosine squared minus sine squared alpha. I'm going to do a derivation of the half angle identities because if you can see the derivation, it is so much more memorable. I think when you just memorize these, it's easy to, wait a minute, is that right? Did I remember it right? If you do this, you can always figure it out. I think this really helped me to remember them. So I have cosine squared 2 alpha equals cosine squared alpha minus sine squared alpha from the double angle identities that we proved from the sum identity for cosine. Now if I let theta equal 2 alpha, then it follows that alpha is equal to 1/2 theta. And I get a half angle identity, right? Because now these will be cosine and sine of half an angle, and this will be cosine of an angle. Let's see what I get. I get cosine of theta equals cosine squared a half theta minus sine squared a half theta. And now remember from the Pythagorean identity that sine squared is 1 minus cosine squared. Let's call this equation star. And I can rewrite this as cosine theta. I can drop the parentheses when they're clear. Is cosine squared 1/2 theta minus 1 minus cosine squared a half theta. Well, now I've got minus and minus is plus, so I've got two of these. Cosine theta is equal to cosine squared of a half theta minus 1. 2 cosine squared of a half theta. There's two of them. And now I add 1 and divide by 2, and I come up with cosine squared of a half theta is equal to this one plus 1 over 2, cosine theta plus 1 over 2. Well, if cosine squared is this number, it's like when you say x squared equals 4. What are the solutions? X is plus or minus the square root of 4. It's plus or minus 2. Same thing here. If cosine squared is this number, it follows that cosine 1/2 theta itself is plus or minus the square root of 1 plus cosine theta all over 2. So you take the square root of each side plus or minus, and get this is a half angle identity for cosine. Cosine of 1/2 theta is plus or minus the square root 1 plus cosine theta over 2. Can we get a half angle identity for sine? We sure can. Also from star. If we instead replace cosine squared with 1 minus sine squared using the Pythagorean identity, then we have cosine of theta equals 1 minus sine squared theta, a half theta, replacing cosine squared of a half theta, and then minus this sine squared theta, half theta. And we have minus 2 of those, so cosine theta is equal to 1 minus 2 sine squared a half theta. And now, if I add this one over here and subtract this one over here, I get 2 sine squared of a half theta equals 1 minus cosine theta. Divide by 2 and take the square root. Well, let's divide by 2 first. Say sine squared 1/2 theta equals 1 minus cosine theta over 2. And if sine squared is equal to this, then sine is equal to plus or minus the square root of this, and we get finally that sine of a half theta is equal to plus or minus the square root of 1 minus cosine theta all over 2. There is a half angle identity for sine. Well, if we have a half angle identity for sine and cosine, we've immediately got one for tangent, right? Because minus square root 1 plus cosine theta over 2. The square root 2 and the top and bottom cancel. The plus and minus don't, because sometimes this is plus and sometimes this is plus, sometimes this is plus, sometimes this is minus, sometimes that's minus and that plus, or minus and minus. It depends on what quadrant you're in, so they don't necessarily cancel. And so what you get out of here is that the tangent of half an angle, depending on which quadrant you're in, you can get plus or minus, is plus or minus square root 1 minus cosine theta over 1 plus cosine theta. There are other versions of these, actually. I like these the best because they're the easiest to figure out from the ones you have. So I'll give these for now and say, these are almost the same, right? These are easy to memorize, this form, because if you can memorize this one, sine is at 1/2 theta is plus or minus square root 1 minus cosine theta over 2. All you have to do is change minus to a plus to get the half angle identity for cosine. And all you have to do then is to take the quotient of those, the 2's canceling, square root 2's, and you get this one. So they're kind of easy. It's just like memorizing a little over one of these to be able to get all three of them. So memorize at least these three. Take a look at the other three in your book. We'll mention those as we go along here. And these will be called the half angle identities, since they express the cosine, sine, and tangent of a half angle. Just as we did with the double angle identities, we won't worry about the secant, cosecant, and cotangent. All you have to do for those is take 1 over these. For instance, if you want the cosecant of a half theta, one way to do it is to take 1 over the sine of a half theta. You turn this one upside down, write plus or minus square root of 2 over 1 minus cosine theta. So there are identities for those. We won't memorize those because we can always figure them out, right? Now, I like your book's presentation on this. I want to do just a little bit out of what the book has, and then a little bit out of the UCO supplement here. Let's see, that's the supplement. Here's the book's other renditions. I wanted you to see these other things. Memorize at least these three, right? But also, it turns out that you can rewrite these. Tangent alpha over 2 can be written as sine over 1 plus cosine, or 1 minus cosine over sine. Those get enough mixed up that I think those are less important, but these are used. You should recognize when you go on to your next course, sometimes they'll write a half angle identity for tangent. They'll say, wait a minute, I haven't seen that before. Well, just remember there are other forms like this. It's nice to have seen them before and realize it's just another alternative to writing a half angle formula this way. Here is a nice example in your textbook of one thing you can do with the half angle identities. We said with the double angle identity, or the sum of difference identities, we can actually find the sine and cosine or any trig function of a multiple of 15 degrees. This will give us another alternative. Any angle that's a multiple of 15 degrees is half of a special angle, and so we can use a half angle to evaluate it. Suppose I want to take the sine of 15 degrees. Since 15 degrees is half of a special angle, we can say, well, the sine of 15 degrees is sine of 30 degrees over 2. By the half angle identity, that's 1 minus cosine of the whole angle, 30 degrees over 2, right? So we're saying sine of 30 over 2 is square root 1 minus cosine 30 over 2. Why didn't we put the plus or minus on there? Well, because 15 degrees in the first quadrant, and the first quadrant sign is positive. So you choose the plus or minus according to what quadrant you're in. Now, cosine 30 degrees we know is square root 3 over 2. And here comes the hard part. Sometimes the algebra in this section is harder than the trigonometry, to be honest. Remember the rules for algebra? You don't leave it like this, or there's a point off on your test, maybe 2 at this point. You have a quotient of quotients. We want to get rid of the compound quotient. So what do? We multiply by the least common denominator of the compound quotients, which is just this one here, 2. We'll multiply top and bottom by 2, and write this as 2 minus square root 3. When you multiply the top 3 by 2, this is 2, and this is minus square root 3, and then the bottom becomes, they put it differently than I would have. I would have put this as 4 on the bottom. Anyway, it comes out to, I would omit this step and say multiply the bottom by 2, and you get square root 2 minus square root 3 over 4. And now the square root 4 on the bottom is 2. And so this is just the square root of 2 minus square root 3 over 2. One warning on this, if you compare this with what you did with the sum of difference identities, right? You could also compute the sine of 15 degrees by writing 15 as a difference of special angles. You can write it as the sine of 45 degrees minus 30 degrees. Use the difference identity for sine and you get an answer, and it will look different than this one, amazingly. How can we get two different answers? Turns out they're not different. They look different. This one been with a lot of algebraic manipulation to be made to look like the other one, or if you're running the calculator, you get the same decimal, you'll see. But don't worry if it doesn't look the same as the answer you got using the sum of difference identities. It actually is the same, it's just complicated algebra to make them look the same. So don't expect the same answer you got in that section, but don't expect it to look the same, but it will be the same answer. All right. Here's another fun one. Suppose the tangent of alpha, some unknown angle, is 8/15. I can use the half angle identities to find the sine, cosine, and tangent of half that angle. If I know actually a trig function of any trig function and a quadrant, here I know alpha is in quadrant 3, it turns out I can find the values, the trig functions, all 6 trig functions of the half angles too. So we'll do sine, cosine, and tangent again in this section. We'll just do those 3 and we'll say the other ones you just take the reciprocals of these and it's no big deal. Alright, so if the tangent of alpha is 8/15 and alpha is in quadrant 3, we can draw this nice picture. Draw alpha into quadrant 3 to make the tangent 8/15. How can we do that? Well, that means we have to make the ratio of y to x, tangent is y over x, 8 to 15. So we'll make 8 in this direction and 15 in this direction. And actually it's minus 8 over minus 15. The minus is canceling, makes the tangent 8/15. And then when you compute this side by the Pythagorean theorem, square root of 15 squared plus 8 squared turns out to be 17. You have a triangle right here. So from the fact that tangent is 8/15, draw the triangle of the third quadrant with minus 15 and minus 8, so the ratio of y to x is 8/15. Then find the last side by the Pythagorean theorem. Then you can calculate all the trig functions of that angle. For instance, the sine is the y over the hypotenuse, so it's minus 15 over 17. I'm sorry. Oh, I'm sorry, the y is 8, yeah, minus 8. Just misread it. Minus 8 over 17, and the cosine is the x-coordinate over the hypotenuse is minus 15 over 17. Now you've got sine and cosine. All you really needed to evaluate actually was cosine here, because now if you want to evaluate for part A, the sine of alpha over 2, use the half angle identity. It's plus or minus the square root of 1 minus cosine alpha over 2. So here's what you do. Given one trig function, you can find all 6 by drawing a triangle. All you really need is cosine for these half angle identities. So if you calculate that one, then you plug them into the half angle identity. Sine alpha over 2 is plus or minus square root 1 minus cosine of minus 15/17 all over 2. And then it's a lot of algebra. This is 15/17. I'm sorry, 17/17 plus 15/17 is 32/17 on the top, all over 2. You can write that as 32/17 times a half, or 16/17 square root. Well, square root of 16 is 4. This whole thing comes out to be plus or minus 4 over square root 17, and then is it plus or minus? Now there's a little trick in here. If alpha was in the third quadrant, I write it in here between 180 and 270, you divide this inequality through by 2, and that means that 90, 1/2 of it, 180 is 90, it has to be less than or equal to alpha over 2, it has to be less than or equal to 270 over 2, which is 135. Alpha over 2 is in the second quadrant between 90 and 180, in particular between 90 and 135, but it's over here somewhere. That means that the cosine has to be negative and the sine has to be positive in quadrant 2. So we have to pick the positive sign since alpha over 2, not alpha, is in quadrant 2. So the sine of alpha over 2 we know is plus or minus 4 over square root 17. Since we're in quadrant 2, it's plus. Similarly, if we want to evaluate the cosine of alpha over 2, well, we just state by the half angle like this, plus or minus the square root 1 plus cosine over 2. Cosine we calculate was minus 15/17. We reduce the fractions and find out that the cosine of alpha over 2 is plus or minus 1/17. Remembering that alpha over 2 is in the second quadrant, the cosine is actually negative, so this time we put the negative sign instead of the positive sign and get minus 1 over square root 17, or minus square root 17 over 17 if you rationalize the denominator. Then tangent alpha is easy. You just take the alpha over 2 is easy. You just take the quotient of those two. I'll just leave out these steps and say, oh, it's the sine over the sine of alpha over 2 over cosine alpha over 2. It's plus square root 32/17 over minus square root 2 over 17, and when you cancel it out, you just get minus 4. So there's how to take the find the sine, cosine, and tangent of a half angle given a trig function of a whole angle of any sort whatsoever. Let's try a couple of the ones from the supplement now. These are the ones I want you to be able to do for the test, right? You have to be able to do ones like this. What if I needed to evaluate exactly the sine of pi over 8? Not only will the half angle identities allow you to do any multiple of 15 degrees like the sum and difference identities did, it will actually allow you to do exactly a trig function of half of any angle you already knew. So you knew how to do 30 degrees, you can do half of that and get 15 degrees. You can do this half angle identity again and get trig functions of 7.5 degrees, or half of that, or half of that. And here we're asking what's the sine of half of 45 degrees, right? Pi over 4 is 45 degrees. This is the sine of 22.5 degrees. We can do that exactly by a half angle identity. Let's turn this off for a second. What is the sine of pi over 8 exactly by hand? Your calculator, by the way, if a fancy calculator can check your answers on this. So on the test, I'm going to ask you to do something related to this that you maybe can't use your calculator on, or to show the steps. But if I want to evaluate the sine of pi over 8, I can say, well, that's the sine of 1/2 pi over 4, right? By the half angle identity, thinking of this as alpha, the sine of 1/2 alpha is plus or minus the square root of 1 minus cosine alpha all over 2, where alpha is pi over 4. I know what the cosine of pi over 4 is from the unit circle, or since it's a acute angle, I just use the triangle, right? If this is pi over 4, then this is square root 2 over 2, square root 2 over 2 is 1, and the cosine is this over this is square root 2 over 2. So this is plus or minus the square root of 1 minus square root 2 over 2 all over 2. And I have the same problem as before. The algebra is harder than the trig. I have these compound quotients. I can get rid of them by multiplying top and bottom by 2. And I'll get square root of 2 minus square root 2, multiplying this by 2 and this by 2, all over 4 on the bottom, multiplying the bottom by 2. I have to multiply the top and bottom by the same thing, or I'll change the quotient. Now is it plus or minus? Pi over 8 is in quadrant 1, right? All the trig functions are positive there, so I could have just immediately done this. And I'll get this plus this number. Well, square root of 4 can be simplified, so I really should write this as square root of 2 minus square root 2 all over 2. And in fact, if you think about it, this is the first problem we just did, just done in radians. So we got the same answer. All right. Let's look at the next one here. If you want to be able to do half angles, half of any special angle, you can now evaluate exactly using a half angle identity. Here's another problem that comes up. Suppose I have this figure here, and I want to evaluate half angles. Like I have a 5, 12, and here's alpha up in the corner. We did one of these last time for a double angle. What if I wanted to find the sine of alpha over 2, given a triangle here? Alright, so this is a 5, 12, and alpha up in the corner triangle. I want to find the sine of alpha over 2. the sine of alpha over 2 is to evaluate the half angle identity. This is plus or minus square root 1 minus cosine alpha all over 2 by our half angle identity. I don't even know what alpha is, but I can still do this. And now it's a plus or minus. It's very easy. In a triangle, a right triangle it is, the two non-right angles are always acute, right? Three angles add up to 180, so these add up to 90. Each one has to be less than 90. It's a first quadrant alpha. It follows that we have a plus here. Now, cosine alpha is this side adjacent to alpha over this side. What's this side? Pythagorean theorem, square root of 5 squared plus 12 squared is 13. So the cosine is 5/13, so I can rewrite that the sine of alpha over 2 is 1 minus 5/13 over 2 square root. If I again get rid of the bad denominator, the compound quotient, by multiplying this time top and bottom by 13, I get 13 minus 5 all over 13 times 2 is 26 is the sine of alpha over 2. Well, this is square root of 826. These both have a factor of 2 in them. We can rewrite this as square root of 4/13. And then 4 is a perfect square, so we rewrite this as 2 over the square root of 13. And this is a fine answer for the test, but if you want to rationalize the denominator, you write it as 2 square root 13 over 13. Either one of those will be acceptable, since this is simpler to write than this one. Well, try some of these problems. See if you can do the rest of them. I'd like you to finish this section this week. We want to have the test soon on chapter 7.